Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. The fundamental problem of supercomputing was to discover how to solve the toughest problems arising in mathematics, science, and engineering, and to discover how to solve those grand challenge problems across an ensemble of processors that were identical to each other and that shared nothing between each other, with each processor operating its own operating system. The latter was the biggest scientific question in the unknown world of the supercomputer. The concrete, measurable, and visible proof that I was in the terra incognita, or in the unexplored territory of the supercomputer, was that it made the news headlines that I experimentally parallel processed and communicated across a new internet. After my invention of practical parallel processing, I became well known, but not known well. That is, many knew Philip Emeagwali as an inventor, but few understood his invention. It's easier to recognize my face than to understand my abstract contributions to mathematics, physics, and computer science. Who is Philip Emeagwali? I am the computational mathematician that contributed to a greater understanding of how to execute the fastest floating point calculations of arithmetic. I am the research mathematician who figured out how to solve the largest system of equations of algebra that must be solved to discover and recover otherwise elusive crude oil and natural gas. I am the mathematician that invented new partial differential equations of the calculus of extreme scaled petroleum reservoir simulation. For those reasons, I said that I am well known as a supercomputer scientist that contributed to the development of the computer, but I am not known well as a mathematician that contributed to mathematics. It's easier to understand that I contributed to the modern computer or to the modern supercomputer that's an internet than to understand my contributions to computational mathematics and even computational physics. Most people think calculus is difficult to understand. The invention of the fastest computer is easier to recall than the invention of the most advanced expression in calculus that in turn is the recurring decimal in nearly all the workloads of supercomputers. A 12-year-old writing a school report, a school inventor report on Philip Emeagwali, cannot explain to her teacher how the new 9 partial differential equations that I contributed to calculus is more accurate than the previous equations in textbooks. On the other hand, she could explain my contributions to the development of the supercomputer, that is a new internet. The technology called practical parallel processing that I discovered on the 4th of July 1989 was called a grand challenge for a good reason. Because it was a once impossible problem that was in the realm of science fiction. The machinery was abandoned by 25,000 supercomputer scientists that were only at home with scalar and vector processing. I was the only full-time programmer of the 1980s that was at the frontier of the most massively parallel supercomputers. In the 1980s, attempting to harness 64 binary thousand processors and to use them to solve the biggest scientific challenges evoked a sense of foreboding. In the 1980s, harnessing 1 billion processors that defined and outlined a massively parallel supercomputer and using them to solve a grand challenge problem was as science fiction as sending an astronaut to planet Mars. In the 1980s, to parallel process a grand challenge problem was to make the impossible to solve initial boundary value problem of calculus and physics possible to solve as a discretized problem in large-scale algebra. The reason I parallel processed alone was that I was the only person with the confidence to do so. In the 1970s and 80s, practical parallel supercomputing across a new internet that was a new global network of 65,536 processors was like shooting at as many birds in the dark. I parallel processed to discover speeds in computation and communication that were previously unseen and that made the news headlines in 1989. Supercomputer scientists that had seen me daily in the 1980s first read about my discovery of practical parallel supercomputing and read about it in newspapers instead of hearing about my discovery from me. For me, as a lone supercomputer scientist, breaking the speed records in both computation and communication, and breaking those records alone, and breaking those records for the first time, and breaking those records with a parallel processing machinery was the metaphorical equivalence of being the first solo mountain climber that climbed to the peak of Mount Everest. The significance of reaching the top of Mount Everest and being the first person to reach it was an achievement in geographical exploration that redefined the boundary of the reachable regions of the earth. I was in the news headlines because I was the first lone wolf supercomputer scientist to climb to the peak of the Mount Everest of massively parallel supercomputing across a new ensemble of 65,536 tightly coupled commodity off-the-shelf processors that shared nothing between each other and that were equal distances apart from each other. Prior to my experimental discovery of practical parallel supercomputing and my discovery of how to solve a grand challenge problem and how to solve it across a new internet. The fastest computations were recorded on the scalar supercomputers of the late 1940s through early 1970s. The fastest computations were also recorded on the vector supercomputers of the mid-1970s through late 1980s. I first entered into the world of scalar supercomputing on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States. That scalar supercomputer solved only one initial boundary value problem of calculus at a time. The ensemble of 65,536 processors that I programmed in the 1980s and programmed as a new internet and that made the news headlines in 1989 solved 65,536 initial boundary value problems at once. Initial boundary value problems of calculus are at the foundation of computational physics. 9 in 10 supercomputer cycles consumed in the 1980s were consumed by extreme scale computational physicists. Extreme scale, high resolution computational physics is executed across a massively parallel supercomputer that occupies the space of a soccer field. For that reason, computational physics is a branch of physics that lies between theoretical and experimental physics. That is, computational physics is the third branch of physics. That branch of physics is midway between theory and experiment. That branch of physics encompassed both theory and experiment. My experimental discovery of how to solve many initial boundary value problems that are governed by a system of partial differential equations of calculus and governed by its companion and discretized system of partial difference equations of algebra, and my discovery of how to solve them at once opened the door to the parallel supercomputer that is the world's fastest supercomputer that achieves its record-breaking supercomputing speed by solving millions upon millions of initial boundary value problems and solving them at once. In computational physics, my experimental discovery made it possible for the supercomputer of today to reduce the time to solution of the biggest scientific challenges and reduce it from 10.65 million days or 30,000 years to just 1 day. Without parallel supercomputing, a global warming prediction will occur 30,000 years after the said global warming occurred. My quest for the fastest speeds in computing demanded that I parallel process across a new internet that is a new global network of 64 binary thousand processors. In the 1980s, massively parallel processing defined the boundary of the supercomputer. The reason I am well known but not known well was that I was the first person to enter into the terra, into the unexplored territory, where the fastest computations can be executed across a new internet. The proof that I entered into that unexplored territory was that I recorded speeds in supercomputing that were previously unrecorded. That contribution made more news headlines than any singular contribution made by an individual to the development of the computer. In the 1970s and 80s, the complete knowledge of the parallel supercomputer was out of the reach of human beings. That is, I parallel processed in that new frontier of knowledge and did so without a map or a textbook. On the 4th of July, 1989, I became the first person to provide practical, in-depth, and easy-to-understand explanations of how to harness millions of processors and how to use those processors to solve a real-world problem that is chopped up into millions of smaller problems. My invention of practical parallel supercomputing made the news headlines because I also discovered how to harness the new supercomputer to solve grand challenge problems that will be otherwise impossible to solve. In the history of computing, the invention of parallel supercomputing is the biggest change in the way we think about the supercomputer. In the old way, the fastest supercomputer solved only one problem at a time or in sequence. In my new way, the fastest supercomputer solved 10 million problems at once or in parallel. I was in the news because I discovered how to experimentally perform 65,536 synchronized parallel communication that was as many times faster than your email. The supercomputer that I programmed in 1974 only computed sequentially and did so within only one central processing unit. The virtual supercomputer that I programmed in the 1980s computed in parallel and did so in the plural senses and communicated across a new internet that is a new global network of 64 binary thousand processors. Who invented the internet? The internet has many fathers and mothers, as well as aunts and uncles. We can only have one father of the internet that invented a new internet. The father of the internet should at least invent a new internet. I am called a father of the internet because I am the only father of the internet that invented a new internet. I invented my new internet by first theorizing it back in 1974 and then continuously developed it for the subsequent 15 years and developed that small copy of the internet and did so until I actualized it as the fastest computation back on the 4th of July 1989. My two raised to power 16 commodity off-the-shelf processors were tightly coupled to each other and were equal distances apart from each other. I mathematically visualized my 64 binary thousand processors as tightly encircling a hyperglobe that is bounded by the hypersurface of a 16-dimensional hypersphere that is embedded within a 16-dimensional hyperspace. I visualized the physical and mathematical domains of my extreme scale high-resolution general circulation model as the 62-mile deep hyperspherical shell that was bounded by two hyperspheres. The inner hypersphere has a diameter of 7,900 miles that corresponded to the surface of the Earth. The outer hypersphere has a diameter of 7,962 miles that corresponded to the outer boundary of the atmosphere of the Earth. I visualize the 2 raised to power 16 vertices of my hypercube to be midway or 31 miles between those two hyperspheres. I drew parallels between my new internet that was a new global network of processors and how I envisioned simulating global warming. My two hyperspheres were parallel to each other. My two hyperspheres extended in the same direction. My two hyperspheres never converged or diverged. My 65,536 processors were paralleled with respect to the climate model that I divided into 65,536 smaller climate models. Those climate models were identical in domain size. My discovery of practical parallel supercomputing created a paradigm shift on how we look at the computer and the internet of tomorrow. Practical parallel supercomputing led to my new definition of the supercomputer as powered by millions upon millions of processors rather than one singular processor. Practical parallel supercomputing was mocked, ridiculed, and rejected during the 67 years onward of its first conceptualization that occurred in print back on February 1, 1922. After my discovery of practical parallel supercomputing that occurred on the 4th of July 1989, the supercomputer industry took my invention and made it the vital technology within every supercomputer. But for the 67 years prior to my invention, practical parallel supercomputing remained in the realm of science fiction. My contribution to the development of the computer is this. I upgraded the parallel supercomputer from science fiction to non-fiction. I discovered how to maintain a one-problem-to-one processor correspondence or analogy between the smaller general circulation models and the processors. I discovered how to communicate synchronously and how to compute simultaneously and how to communicate and compute and do both 65,536 times faster and do both on 65,536 central processing units and across 16 times as many email paths. In other words, I paradigm shifted in my email communication across my new internet. I discovered how to harness processors and how to shift from the singular person-to-person email to the plural processor-to-processor emails that I synchronize across my new internet that is a new global network of 65,536 tightly coupled central processing units. That new global network defined a parallel supercomputer that is a new internet de facto. I invented a new internet that tightly encircled a hyperglobe. My hyperglobe is shaped like a 16-dimensional hypersphere in a 16-dimensional hyperspace. My supercomputing paradigm shifted because I computed simultaneously on 65,536 central processing units and emailed synchronously across 1 binary million email wires. That was how I discovered that practical parallel processing must be vital to the supercomputer that solves many problems at once or in parallel. That invention of practical parallel supercomputing embodied the Philip Emeagwali formula that then US President Bill Clinton praised in his White House speech that was delivered on August 26, 2000. President Bill Clinton recognized my contribution to the development of the parallel supercomputer in part because it made the news headlines 11 years earlier. That contribution was my experimental discovery of how to record the fastest computations and how to record those fastest computations and record them across a parallel supercomputer. I recorded those fastest computations by solving 65,536 problems at once instead of solving only one problem at a time. I'm often asked, what is Philip Emeagwali known for? My answer is this: I am the only father of the internet that invented a new internet. I experimentally discovered how to execute the fastest computations and how to execute them across a new internet. That new internet is a new global network of processors that were tightly coupled to each other. I visualized the processors of my new internet to be equidistant from each other and to be evenly spread out across the surface of a globe that I also visualized as embedded within a 16-dimensional hyperspace. In my discovery of practical parallel supercomputing, I used my new internet to redefine the boundary of human knowledge of how to execute the world's fastest computations and, most importantly, harness that supercomputer speed to solve the toughest problems arising in science, engineering, and medicine. My experimental discovery of practical parallel supercomputing that occurred on the 4th of July 1989 of how to reduce the supercomputer time to solution of grand challenge problems and reduce it from 180 years to just 1 day, in effect distinguished between what's computable and what's not computable. Climate models must be used to accurately foresee otherwise unforeseeable long-term climate changes. In theory, extreme-scale high-resolution climate models are computable, but in practice, a climate modeler may need to run more than 1,000 accurate simulations. If each accurate simulation of the planet's climate has a time to solution of 180 years, then the climate modeler that began her simulation 2 millennia ago, or in the year Jesus Christ was born, will complete her forecast in nearly 2,200 millennia from now. I was the first computational physicist to experimentally discover how to parallel process across an internet. I was in the news headlines because I discovered how to parallel process extreme-scaled computational fluid dynamics codes and how to simultaneously execute them in parallel and how to synchronously email them across a new internet. I was the first person to experimentally discover how to reduce 180 years of time to solution of a grand challenge problem being solved on one computer to just 1 day of time to solution across a new internet that is de facto one supercomputer. That new internet is a new global network of 65,536 identical central processing units that I visualized as equal distances apart from each other and on the surface of a globe that I mathematically visualized as embedded within a 16-dimensional hyperspace. Along my way to that terra incognita called parallel supercomputing that was then an unknown and unexplored territory that had no map, I employed a system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations of calculus that encoded a set of laws of physics, including the second law of motion. I used those partial differential equations to formulate 65,536 initial boundary value grand challenge problems. I discretized those grand challenge problems of calculus to obtain a set of linear equations of extreme scale algebra. I reduced calculus to algebra because algebra is the only way the supercomputer can experience the laws of physics. Those linear equations were at the algebraic core of my extreme scale computational fluid dynamics codes. I executed my 65,536 codes in parallel and across as many tightly coupled processors. In a manner of speaking, I used those 65,536 processors to poke my nose into the laws of physics and to discover how the millions upon millions of processors that powers the modern supercomputer can be harnessed and used to foresee the otherwise unforeseeable climatic changes. I discovered that I can use those 64 binary thousand processors that outlined and defined my new internet, and that I can use them as one cohesive supercomputer that can execute an extreme scaled high-resolution global circulation model. Parallel supercomputing is a precondition to foreseeing global warming. My contribution to the development of the computer is this: I redefined the boundary of what the computer can compute, and I redefined that boundary by a factor of 65,536.
insightful and brilliant lecture.